All right. So yes, thank you for, I just need to thank the organizers or the organizer. I don't see Sohail in the room right now, but I really appreciate all the work he does into organizing these meetings each year. And um, yeah, I hope hope everything carries on in the future. I'm sure it will. And yeah, what I want to talk to you is about a project that we've been working on in my lab for a couple of years, entitled From SELEX to Sensor. And it really combines a lot of work that I do in my lab. Well, not me personally, but my students do, as well as collaborations with our lab that does the sensor part, Phil, Philippe Dauphin Ducharme at University of Sherbrooke. So just an introduction to what I do. I my my goal is to study how aptamers function, and I really just focus on DNA aptamer, small molecule interactions. And I don't do SELEX. I don't make sensors, but my research involves what the in-between part is between doing SELEX and making a sensor, and biophysically characterizing aptamers in terms of, I have to measure their affinity of binding using isothermal titration calorimetry. I really enjoy this technique, and that is a labelless strategy. It's in solution, and you get the whole affinity and thermodynamics of binding from the experiments. I have ventured into looking at aptamer stability and binding using differential scanning calorimetry. And I also do NMR spectroscopy, not so much looking at three-dimensional structures, but rather looking at binding as monitored by NMR. And I will say a lot of my early work has focused on looking at the classic cocaine binding aptamer, but I'm not actually talking about the cocaine binding aptamer today. So in terms of sensor, the sensor part is done as a collaborative project with Phil in Sherbrooke. He uses this electrochemical aptamer-based biosensor technique developed by Kevin Plaxco. So Phil did a postdoc with Kevin Plaxco and learned how to perform, construct these sort of sensors there. And the idea is, you have one end of the aptamer attached to a gold surface. The other end of the aptamer has a redox supporter, usually methylene blue. So in the figure here, and I won't try and point at the screen. Actually, I can get the laser pointer function and be fancy. There we go. That's okay. So R stands for the redox supporter. And the idea is what you measure, and I am not an electrochemist. I do know reduction and oxidation definitions, but that's somehow my limit. So the redox supporter changes the distance from the free state of the aptamer, which is on the left here, to the bound state of the aptamer on the right here. And the aptamer, so the redox, these EAB biosensors are thought to function because there's a conformational change with binding, or some sort of ligand-induced folding occurring in the aptamer, whereby in the free state, the aptamer is relatively unstructured. In the bound state, the aptamer becomes more structured, and redox supporter has a different distance from the surface, so there's a different electron transfer rate, which is what gets measured. And I think these EAB biosensors are really interesting, especially because a lot of what Kevin Plaxco has been working on recently has been trying to get them functional in vivo for in vivo monitoring of antibiotics, anti-cancer agents, various other compounds, or whatever the aptamer binds, should be able to analyze in vivo. However, it's often difficult to, I'm told, because I don't translate selected aptamers into functional biosensors, but this can be a problematic step. So the whole idea of our project is to try and find out how different aptamers, how you can transform from a selected aptamer to a functioning biosensor, i.e. select a sensor. So we thought of a few things that needed to be shown to make sure that you have a functioning sensor from an aptamer you identified from SELEX. And the first one is you need to confirm that it binds a ligand. Sounds obvious, but it's always good to confirm that you do have binding. And to do this, we use ITC as thermal titration calorimetry. And we also wanted to look at, the whole what's been published about the EAB biosensors is this ligand-induced folding, and you need to have a structural change. And we were using NMR spectroscopy to see if a structural change is occurring. And if we have structural change and if we have binding, how important is this the binding and structural change? How important is this to occur close to the surface, far from the surface? Is there a distance relationship? And, to give away the ending, yes, this is the critical function, that there is a distance relationship between the site of binding and structural change and producing a functional EAB biosensor. So what we did over the last year and a half, probably, Rahith, who's handling the tech here, and Emily, who's at the back there, have analyzed a set of aptamers, small molecule binding aptamers, to see what works. And I'm just going to show an example data from the dopamine binding aptamer. We have a low resolution structure of the dopamine aptamer on the left here and on the right here. And this is doing ITC, giving some ITC data. And you can see both forms, the long stem version of the aptamer and the shorter stem version of the aptamer, both bind. ITC shows there's a difference in affinity, 3 micromolar versus 43 micromolar, but they both bind the ligand. And I will preface this by saying that all the small molecule binding aptamers we look at are from capture SELEX. So they typically have a stem and then the aptamer variable regions up here. So they do almost always contain the stem region. And I'll just show a little bit about introduction to NMR for the purposes of my talk. So when we look at the NMR of DNA aptamers, here's the full spectrum NMR 1D proton NMR spectrum of a DNA aptamer. And we focus downfield on the immunoproton region. And the immunoprotons are found in Watson, in base pairs, from hydrogens protected from exchange with water, typically GC base pairs, AT base pairs, but they could be non-canonical base pairs as well. And here's an example from, I lied, I am showing some cocaine binding aptamer data. Excuse me there. And here's an example of an aptamer that folds upon binding. We have few peaks in the free spectrum, and as ligand adds, peaks appear. And these peaks appear due to structure forming with ligand binding. Uh-oh. Nope, there it goes. It's just a delay. All right. There we go. So aptamer binds. We then looked at the NMR. We have a long stem version on the left and a short stem version on the right. And both aptamers show structural formation with ligand binding, in that there's far fewer signals in the free state. And after you add ligand, you have many more signals appear due to structure forming as the aptamer binds the ligand. The long stem version, where there's more stem structure, we have more Watson-Crick base pairs. In the free aptamer, we just have very few base pairs, if any observable ones at all. But in both cases, we have structure forming with ligand binding. And Phil went ahead and constructed these EAB biosensors. And what we found is that only the short aptamer, 5 base pair aptamer that had 5 base pairs in this stem region, showed no response when a EAB sensor was constructed. But if we delete a few or remove a few base pairs from the stem, we have aptamer that functions well. So only the short stem aptamer functions as the sensor. And there we go. And so we did this with a bunch of other, and I apologize that yes, yellow isn't a great color to use. And we did this with a number of other aptamers. Here's a case where we took an aptamer that the ochratoxin aptamer. I modified my slides earlier today, but I should have corrected this. This is an ochratoxin binding aptamer. The original aptamer, which was, selected by Greg Penner at Neo Ventures, who sponsors the conference, but that was not here, but that's okay. The ochratoxin binding aptamer has 3 base pairs at a stem region before it goes to this quadruplex structure. And we constructed a longer version. So instead of shortening aptamers, we decided to lengthen this aptamer and introduce 3 more base pairs at its terminus, and showed that, ITC, not showing bound, both bound ochratoxin by ITC, both had structure formation with ligand binding. And in this case, the regular OTA aptamer shown in this yellow-green here gave a signal, but when we lengthened the stem, we lost the signal. So we really think that it's the length of the stem, length from the tethered aptamer to the surface is a critical point in producing a functional biosensor, and not because there's structure formation. Structure formation is necessary, but not sufficient to produce an aptamer that functions as a sensor. So we looked at, by we, I mean Rahith and Emily, looked at a lot of other small molecule binding aptamers as summarized here. You can see we have different length of the stem. Caffeine, tryptophan, uric acid. A lot of these were selected by either Milan Stojanovich's lab or Zhuwen Liu at Waterloo. So we looked at these, and to summarize the data, Min Dat in Phil's lab did principal component analysis. And I will preface this by saying I am not an expert in principal component analysis. Happy to present the results. So what we did was look at various factors that we can acquire from all the data. So we have stem length, which is 3 base pairs, 4 base pairs, etc. Enthalpy of binding, entropy of binding, free energy of binding. We looked at quantifying the NMR spectra from the free state to the bound state by looking at the integration of the free versus integration of the bound. And in this rather complicated looking graph, vectors that are 180 degrees relative to each other have a negative correlation. So here's KET, so the rate of electron transfer, which is sensory response. So maximum sensory response is shown by this KET vector, and it correlates strongest with stem length. Shorter the stem length, it's negative correlation, because the shorter the stem length, the greater the response. So that's what we mean by negative correlation, which is what we thought from the data, but no, we have a way of quantifying it. But we also thought that we might get some useful information from looking at the enthalpy of binding or entropy of binding, but all those are relatively 90 degrees relative to each other, which indicates that it is no correlation. we've really looked at this, and I really thought about this more in terms of sensor response, but it kind of makes sense in some ways that the enthalpy and entropy are negatively correlated. If you look at a lot of the literature, there's enthalpy, entropy contra compensation is often done. There's a recent very impressive paper by Yi Zhao from North Carolina, who has a huge data set of ITC binding data, and she showed there was enthalpy entropy compensation. Now, delta G is a reflection of KD, so that's okay. That's not 90 degrees, but it's also not near 100, 0 degrees or 180. So there's not a lot of correlation between affinity and sensor response. And similarly with integration of the NMR peaks is it doesn't correlate well. So really what best correlates is shortening the stem length so that you have your shortest possible functioning aptamer. The binding would have to be in the clinical range for whatever you're trying to analyze, of course. But the shorter the stem length, the maximum sensor response. And all my fancy thoughts about enthalpy and entropy and various other parameters from ITC really doesn't correlate with maximum sensor response, unfortunately. So with that, I think I'm at my end of my talk. And yeah, so ligand, what we can say is ligand binding is reliably, we get an aptamer from SELEX. We tried 8, I believe, and they all worked as a biosensor. So we can reliably get an aptamer from SELEX and capture SELEX anyways, and produce a functioning biosensor from it. Structure, not surprising in some ways because it's a capture SELEX experiment, but structure formation occurred in all the aptamers studied, even the ones that didn't result in functional sensor. But I believe the structure formation needs to occur, but it needs to occur 2 or 3 base pairs from the sensor surface, which is the critical factor. So I'd just like to thank the students from my lab who did the work. From the left is LaShawn, Rahif, and Emily. They all are presenting either talks or posters here, so that's go see their poster, listen to their talk. And I'd like to thank Phil and Sherbrooke for the wonderful collaboration, and Dat from his lab for doing the sensor data. And he'll be talking at the oligos meeting, but he's not actually here, so that's okay as well. But if you're around for the oligos meeting, he'll be there. So thank you, and I'm happy to take questions. So you probably want coffee first. So.
Yeah, so maybe one question, and the rest you can grab at coffee. Okay. Okay, yeah, you were first.
I'll ask you a really quick question. So, and I think that the distance thing is really interesting. So my question is twofold. One is, does anyone know the distance away from the sensor surface that you lose the signal? No, it seems like it's actually a very rapid, very short distance.
It can be, and I'm sure it varies depending on the aptamer.
And the second thing is, should I think about this as being an unstructured aptamer? This end is sort of moving around, but not located away from the sensor, but just sort of flapping around. And then the sensor then finding structural imparts a structure so that now it's in one place, and you can get that increase in Z. Is that the way you're thinking about this?
It's hard to say. At least for your second question, there's, we don't know what the structure of the unbound aptamer in many cases is. For example, here we can see that in the free aptamer we have a few Watson crick base pair signals, and probably this stem is forming. But you can have, I'm not an expert in the sensor construction, but you can have, when you have a 5 CH2s to a thiol at one end, So you could attach it and it could be forming and could be flopping around. I know they put in these they fill in the gaps, or I don't know. You know, it's how the aptamer on the sensor surface looks is very much up in the air. But excuse me, in this case, you know, the structural change that's going on would be far away from the attachment point, the longer the stem gets. So I think the first question was how, we haven't done 5, 4, 3, 2, 1 and looked at it, you know, we might do that in the future. Right now, we were just looking at either long or short, and we pretty quickly came up with short. But, you know, you look at something like the glucose after we're here, and who knows, we don't know where it binds, but you don't know the structure of the stem in the free state. Is it just 2 base pairs, or is it this and including that? So there's a lot of stuff still to be done, but the longer version doesn't work as a sensor, the shorter version does. But yeah, there's a lot of, here we have 2 base pairs in the tryptophan. You know, it would probably still work as 3 base pairs, but we haven't tried it before. Purchased the DNA, but never made a sensor with a 3 base pair. That's yeah, that takes more expensive to buy the phylated and the methylene blue label DNA, so you might strike it rich and be able to do all the different experiments.